All right. So the purpose, guys, of this lab is we want to investigate the signs of a chemical reaction. We want to know what happens in a chemical reaction, right? And what we learned the first day we talked about chemical reactions was this, okay? In a chemical reaction, atoms can be separated, joined, or rearranged. And our products are chemically different than our reactants, okay? That means that we really can't get them back. Okay, once the reaction has happened, we have a new set of materials. Not new elements, obviously the elements are the same, okay? But they're in different combinations or arrangements or whatever on the product side, right? We know that a chemical reaction has occurred because there are certain signs of a chemical reaction, ones that we've talked about: color change, odor change, temperature change, all those kinds of things are all signs of a chemical reaction, all right? So, the problem we're investigating here is that when substances are mixed, the chemical properties of each material determine whether a reaction occurs. What evidence do we have that a reaction takes place when substances are mixed? So we're looking for those signs of a reaction, and what do they mean? Okay, if there's a color change, okay, what does that mean for us? If a precipitate forms, why does this precipitate form? Right? The big reason is because when a chemical reaction happens, the products are chemically different. So they have different properties than the reactants did. Reactants may have both been soluble. One of the products may not be. So it's a precipitate. Everyone kind of follow me on that? Okay, that's why we have those signs of a chemical change. All right, for our design part, identifying our variables. Here's how the experiment's going to work. You will have these different pairs of materials that you will be mixing, 7 different pairs. Okay, so each time we perform the procedure, essentially we're performing it on a different pair of reactants. Okay, so every time we perform this experiment, okay, or a different part of this experiment, we are using a different set of reactants. So we are changing the reactants in this experiment. Okay, each time we combine different reactants, we should see what? What's going to happen? A chemical change is going to happen. What are we going to see when a chemical change occurs? Something, right? One or more of the signs of a chemical reaction should occur. That's what's going to respond to the fact that we are changing the starting reactants. I think not everybody's picking up what I'm putting down here. I'm kind of giving away the answers here if you're paying close attention. Okay, so each time we mix it together a new set of reactants, we are going to get a different sign or several signs of a chemical reaction. That's what's going to respond to that. Now, in terms of things that we need to control in this experiment, okay, anything that can affect how a reaction occurs should be controlled. All right. So one of those things we're kind of passively controlling, same as we were before in the last lab, is the room temperature. Yeah, okay, temperature affects rate of reaction, okay, and that's going to be the same throughout the entire lab, all right? We could also say that other environmental factors, atmospheric pressure, any environmental factors, okay, that you can think of can be controlled variables for this experiment, okay? Now remember, each variable needs to be explained on its own, okay? So the manipulated variable is this because this is what's happening in the lab. The responding variable is this because this is how it's going to respond, okay? Or this is what it's going to do, okay? Everyone follow? We have to have those explanations. We looked at those yesterday. Each controlled variable needs to be explained, and I explained temperature for you already. Temperature affects the rate at which reactions occur. Therefore, it needs to be controlled so that all reactions occur at the same rate. Okay? That's the kind of thing we're looking for. Okay, for our hypothesis, what 3 words go in our hypothesis? If, and, then. Okay, so the if part deals with what happens in a chemical reaction. And I kind of talked about that a minute ago when I stated Dalton's atomic theory, point number 4, about what happens in a chemical reaction. So I would say that the if part of your hypothesis, okay, should talk about what Dalton says what Dalton says happens in a reaction. Okay, so if in a chemical reaction atoms are blah, blah, blah. Okay. Okay, remember that the and part describes the experiment. That's going to be pretty straightforward, right? Different pairs of reactants are going to be combined in order to observe reactions. That's essentially the and part of this hypothesis. That's what we're doing. Okay, the then part needs to tell people what's going to happen and a little bit about why. Okay, so the then part should probably talk about signs of a reaction and why they occur. All right, and I've talked actually about that several times this morning. Okay, talked about what happens with reactants and products and how they're, how they relate to each other. Right, that's kind of the why part. Okay, so that's what should go in your hypothesis. Everybody good with that? Okay. Now, the next thing we have to do is we're going to look at the reactions that we're going to perform, and we're going to predict them here together. Okay, we're going to predict what those are going to look like. Are we going to be right on all of them? Probably not. So you're going to have to observe carefully. Okay, if some of our predictions aren't right, then we'll have to come back and have a look at why they weren't right after the lab. Okay, so here's some of the stuff you need to know. All the materials are on the front bench. They're actually pushed more over to the right-hand side now because someone left their lab materials over here yesterday. So, okay, all of the unknown materials are over on the right-hand side. Okay, sorry, they're not unknown. They're labeled. Okay, I actually put on what they are so you know what you're mixing together. And on the cart is going to be your thermometers and your watch glass. Okay, your watch glass is this thing here. Okay, that's where you're going to mix the stuff together. So when you come up to the front, okay, and you're looking for pair A, okay, you'll put one of the ingredients of pair A in the watch glass, and you'll take the other ingredient back to your table in the eyedropper. Okay, all of the solutions have an eyedropper. Actually, have two eyedroppers in them. All right, so take the solution, okay, take it back. Okay, one thing will be in here, and then when you get back to your table with your thermometer and everything, mix them together. Okay, thermometer needs to be in when you start the mixing. All right, that way you can observe any temperature changes that occur. Everyone follow? Okay, what do you have to be really, really careful of with those eyedroppers? Right, okay, if you forget which one you took it from, throw it away, okay? They're cheap, all right? Those eyedroppers are disposable, they're cheap. If you forget which one you took it from, throw it away, okay? I don't want the reaction occurring in the source, because there's a lot of it there that could be a bit more energetic than I would like, and then I have to remake the sample, and those are expensive. Okay, eyedroppers are cheap, samples are not. All right, so if you forget, that's fine. Just throw it away, and when one is short, I'll put more in it. Okay, everybody with me there? Okay, super important on that one. Okay, when you have performed the reaction and done your observations and everything like that, okay, then you need to rinse off the watch glass in the nasty bucket. Okay, so just take it over there. I've put 2 bottles of distilled water, okay, inside the fume hood where the nasty bucket is, okay, and just rinse it off into there. Get most of it off and into the bucket. Then you can rinse it in the sink and paper towel dry it and get ready for the next pair. Everyone okay with that? All right, so here are our pairs. All right, so you've got this. You'll want to fill this in a little bit, okay, on yours. So you've got this exact table there on the paper in front of you. You also have it on your Chromebook. You can choose where you want to do it, okay? All right, so for pair number 1, I'm mixing sodium hydroxide with ammonium chloride, okay? Now, just looking at this, what kind of reaction should that be? It should be a double replacement. They're both ionic compounds. Okay, so in this one, I should just swap the metals, remembering that ammonium is positively charged and behaves like a metal. Right? So that means that ammonium should end up with hydroxide, and sodium should end up with chlorine. Okay, be hard to determine what the signs of that reaction might be. Okay, double replacement reactions oftentimes produce precipitates. Okay, they oftentimes produce color changes. Okay, sometimes they'll produce temperature changes. That's what we know for right now. All right, is that reaction balanced? Not that that's really important here in the predicting, but yes, it is. Okay, next pair. This is a weird chemical. Okay, because it's a weak acid, it is written backwards. Okay, realistically, because it is an ionic compound, it should be written like this: HCH3COO. This is the plus and this is the minus. Okay, the CH3COO is called acetate. So this stuff is acetic acid, commonly known as vinegar. All right, now this is not your store-bought vinegar. This is glacial, practically glacial, acetic acid. Okay, I took it out of our main glacial sample, which means absolutely 100% pure acetic acid, and I diluted it slightly because I like my samples to be uber concentrated, because then reactions are obvious. Okay, so this stuff is super concentrated. It will eat a hole in you. Okay, so be careful with it. It's not vinegar. Smells like vinegar, like way stronger than vinegar, like give you a bloody nose, knock you on your butt. Smell like vinegar, but okay, be careful with it. It's super concentrated. Okay, that means don't squirt the little eyedroppers except into the reaction container. Okay, all right, so this is acetic acid. Okay, and it's reacting with sodium hydrogen carbonate, which is more commonly known as baking soda. You've done this reaction a million times. Okay, you know what's going to happen, right? But it should be a double replacement reaction. This is an ionic compound with hydrogen acting as the metal, and this is an ionic compound with sodium acting as the metal. So what I should see is something like this: sodium acetate, and I should see hydrogen carbonate. Okay, something like that. If it's a true double replacement reaction, that's what I should see. And that is also balanced. Okay, now, that's the way I predicted it. You've mixed vinegar and baking soda lots of times. What usually happens? Yeah, it bubbles and fizzes. What's that usually evidence of? Okay, are any of those things a gas? Ionic compounds are crystalline solids at room temperature. They're not gases. So this is what we predicted. Might not be right. We have to observe that and see. All right, pair number 3. Okay, I've got sodium hydroxide. So I'm using sodium hydroxide in more than one reaction. Okay, and I'm mixing it with magnesium chloride. What kind of reaction is that? Also double replacement. We've got a lot of double replacement reactions here. Okay, so we've got NaOH is going to react with MgCl, which will leave us with NaCl plus MgOH. Okay, they're both ionic compounds, so this one will need a 2 because it's dropped and swapped differently, and then I would have to balance like that. Okay, so that's our prediction. Okay, hopefully that one works out the way it should. All right, I think the other ones you can handle. Okay, I think you can handle pair 6 and pair 7. I think you can handle the prediction for that on your own. You don't have to predict pair 4 and pair 5. Okay, the reason you don't have to predict pair 4 or pair 5 is because they are an indicator reaction, right? And you don't even talk about those until like Chem 30. So those are just ones where you're going to mix them together and observe the reaction. Okay, tell me what happens in the reaction. Okay, now in this reaction in pair 4, okay, you are mixing together in pair 4, you are mixing together sodium hydroxide and phenolphthalein. Okay, now the phenolphthalein is actually going to come in a small squeeze bottle, okay, labeled phenolphthalein. So okay, you can see it here. It's C20H14O4. Okay, we have it in solution. Okay, phenolphthalein, if you've ever watched like any of the like CSI kind of shows, it's the stuff they use to detect the presence of blood. All right, so if they swab something and then they drop that clear stuff and the swab turns pink, okay, that's phenolphthalein. Phenolphthalein changes color depending on pH, and it happens to change color right around the pH of normal blood. Okay, so if it's slightly basic, it turns pink. Okay, if it's acidic, it goes clear. Right, so that's what we'll be looking for there. Okay. All right, so in pair 4, and this is really important, in pair 4 you're going to mix sodium hydroxide with the phenolphthalein and observe what happens. Okay, since it's an indicator that changes color, I would think color change is probably what we're watching for, but we should still take the temperature. Then you can't throw that away. Pair 5 is going to use the product of pair 4. So you're going to keep everything from pair 4 and you're going to go back to the table and you're going to get acetic acid. Okay? And then you're going to add the acetic acid to the solution you made and see if anything else happens. Ideally, it should hopefully change back, okay? Because you have a basic solution and you're going to add an acid and try and change it back. All right, so that's what we're looking for there. Okay. Right, that should take care of what we need to do for the lab part. Okay, when you first get over there, get your safety goggles on. Okay, might not be a bad idea to put on a lab apron. Okay, they're hanging on the wall just when you come in on the right-hand side. Okay, because like I said, this stuff is all concentrated, quite concentrated. Okay. All right, any questions before we go across? Okay, take the sheet I gave you. So you have the pairs. Okay, you have the directions as well as the observations table to fill, and then you can come back and fill it in on the Chromebook when we're done. Any question? Oh, yes. You're welcome. Okay, guys, so you can head straight across to the chem lab. I unlocked it already. So when we perform these combinations, and we actually saw and kind of experienced what happened, okay, for pair number 1, what did we notice? Really strong smell. Oh, just put it on the front table. I'll put it away. Okay, so there was a really strong smell. A really strong smell usually means what's been produced? A gas. Okay, so if we're looking at how we predicted this reaction, did we predict a gas to be formed? We did not. Okay, so this prediction is not right. And that's fine. It was just a prediction. But what you're required to do in the analysis is you're required to write out the reactions as they actually occurred. Okay, so a full formula reaction and a reaction in words, okay, as they occurred, balanced chemical reaction. So in the analysis then, okay, we've got to figure out what really happened here, right? Because this certainly didn't happen. So here's what I'm going to tell you, because I'm not going to give you the whole thing, but I'll give you at least a way to start it. The gas that was produced in this reaction is ammonia. Okay, that's why it should have smelled a bit like Windex. Okay, like really strong Windex. Okay, so ammonia was the gas that was produced. There are 2 other compounds, and they're both ionic, that were also produced. So this is still sort of a double replacement reaction. It's just not a textbook double replacement reaction. Okay, so here's what you have to do to figure out what else is still left in that reaction. Okay, we know that 1 nitrogen and 3 hydrogens are already accounted for over here. So really, what that means is this nitrogen is gone, and that's what's left. Okay, so now you've got a reaction there that you can predict the products of. You've got sodium hydroxide reacts with hydrogen chloride. Okay, predict the other 2 products. Okay, and you'll have your reaction. Remember, it needs to be balanced. Okay, all of that kind of stuff. We had a similar problem with pair number 2. It bubbled and fizzed, which means it produced a gas. What gas gets produced in that reaction? Yeah, CO2. Carbon dioxide gets produced in that reaction. So obviously what we predicted here is also not right. So one of the products is carbon dioxide gas. There are still 2 other ionic compounds that are produced in that reaction. So we've got to do a similar thing here and figure out what's left after we account for this carbon dioxide. So the carbon dioxide actually comes from here. Okay, so once I eliminate 1 carbon and 2 oxygens from that, what I'm left with is that. So now I have a reaction between HCH3COO, or acetic acid, and sodium hydroxide. All right, so you should be able to predict the products from there and figure out what the other two products are. Okay, I think pair 2 went pretty much like we predicted it, so you got a little freebie there. Okay, and I think the other ones also went pretty much as predicted. So you need to write those reactions out in the analysis and balance them. Okay, so if we're looking at I'll come back to this in a minute, guys. Okay, so in the analysis, okay, question number 1 is, using words and formulae, write the chemical equation of each chemical reaction that occurred. All right, so essentially you have, some of that already done here in our predicting part. Okay, all you have to do is write it out in formula form, so it looks like this, and in words for each reaction except pair 4 and 5. Okay, you don't have to do pair 4 and 5 because those are different kinds of reactions. So you got to do 1, 2, 3, 6, and 7. Question number 2 in the analysis is about solubility. Okay, 2 of the reactions produced precipitates. What you need to do is look at the reactions you wrote for those 2 reactions and decide which of the products was the precipitate. So which one's not soluble? How will you figure that out? Do you have something that you can look at that tells you whether a compound is soluble or not? Okay, remember us using the solubility chart? Okay, so you got to go back to your solubility chart and check out, okay, so which one of my products is not soluble? That's the one that's the precipitate. So I want you to tell me, okay, in reaction whatever, there was a precipitate formed and it was this compound. In this reaction, there was a precipitate formed, it was yellow, and it's this compound. Okay, everybody with me there? All right, so that's what I'm looking for in the analysis. Okay, reactions 1, 2, 3, 6, and 7 written out in formula and word form for number 1. What are the 2 precipitates for question number 2? All right, for your conclusion, copy and paste your hypothesis down to there, and then tell me, can you accept or reject it? Okay, what we were looking for was, are the signs of a chemical reaction there, and what do they tell us? Okay, well, we can conclude, okay, you look at your analysis, okay, were reactions happening? Did they produce new things? What does that say about your hypothesis? Talk about that, couple sentences about that. Okay, sources of error and evaluation, 2 sources of error and ways to fix them. All right, so you can come up with some, okay, that'll work. All right, everybody clear on the expectations for this one? Okay, remember, big thing here was level of detail. Okay, make sure you have a good level of detail, okay, in your explanations for the variables, your hypothesis, your conclusion, okay, things like that. There's not much to write in terms of detail for the analysis. You're writing out chemical reactions in formula and word form. Okay, just make sure you do that, okay, and telling me what the precipitates were. Okay, all right. So for you guys, okay, I have made that due on March 8th. Okay, start a class on March 8th, so make sure you have it done for that day. Obviously, you can come in and ask questions if you want. Okay, I also put the lab observations video on here, so if you were uncertain about any of the combinations, you can watch that video. It's me just doing the lab. Okay, and I will have this podcast posted there right away, so you can listen to it while you're putting the finishing touches on your lab report, making sure you haven't missed anything or you've done all the things you were asked to do. All right, so that'll be on there as well. Okay. Questions on that, guys? Okay, you still got about 10 minutes, so you can get a pretty good start on your lab report here.